Hello, my name's Greg Williams. I am the current president of the Eastern Canada Division of the NMRA. Today, I'd like to share with you some soldering tips, tricks, and techniques, or as our friends over the pond say, soldering. First off, a quick tip on how not to hold your soldering iron. I hope you enjoyed that little bit of humor. So let's get into it. What exactly is solder? Solder is an alloy of lead and tin, most commonly. And because of the magic of chemistry, the combination of these two metals into an alloy have a lower melting point than they do apart. The melting point of lead is 620 Fahrenheit and tin is 450. But if we combine them in the ratio of 63:37, it melts at 361 degrees Fahrenheit. Now, for reasons that do not matter to us in this presentation, we normally use the ratio of 60-40 solder. Now, how exactly does solder work? It's not simply melting a metal onto two other metals. When solder melts on copper, there is what we call a wetting action. What happens is the molecules of the alloy solder merge with the molecules of copper to form a new alloy. You can see that in the illustration to the right. On the top, we have solder, and then we have the intermetallic layer where the solder molecules are mixing with the copper molecules, and at the bottom, we have the copper pad. Without this wetting action, soldering has not occurred. There will be a joint, but not a good one. You might as well use glue. Now, what we have to remember while we're doing that is all metals oxidize constantly. And although the surfaces to be soldered may look clean, bright, and shiny, there is always a thin film of oxide covering it. For a good solder bond to happen, surface oxide must be removed during the soldering process. And for that, we use something called flux. Now, heating metals also causes oxidation to happen even more rapidly. And in order to remove that, flux is used. Now, the flux action is very corrosive at the temperature that solder melts. This removes the oxidation, allowing the solder to flow to get that wetting action and create the molecular bond. In its unheated state, rosin flux is non-corrosive and non-conductive, and therefore it does not affect the circuitry or anything that we are soldering. An important thing to remember is when we're doing electronic soldering, we always use rosin flux. I'll talk more about flux in a little while. Rosin flux melts below the temperature of the solder, removes the oxide, and allows the solder to flow. Rosin flux, the kind we use for electronics, comes in either a paste or liquid form. Most electronic solder is rosin core, which means the alloy, the 60-40 tin lead alloy that we're using, has a core inside of it that contains rosin. As solder is brought up to the heated temperature to melt, the rosin melts first, removes the oxides, and allows the solder to flow, and we get the wetting action. The majority of board soldering does not require extra flux. Here's two examples of flux by MG Chemicals. They are a known and trusted brand of soldering chemicals and solder and various things that are used in electronics. On the left, you see the rosin flux in a liquid state, and on the right, in a paste. Either one works perfectly well, works exactly the same way, and is a matter of personal preference. Let's talk about the soldering iron for a minute, because there's a lot of myths surrounding that. First of all, wattage. Any iron between 30 to 60 watts is more than enough for any soldering that we're going to encounter in model railroading. What's more important than the wattage is the tip temperature. A 20-watt iron or a 60-watt iron both reach a temperature capable of soldering. What the wattage means is it allows the tip to recover faster and also heat a larger area. Doesn't have to be an expensive iron, but don't cheap out. You can go to the dollar store and buy a soldering iron for $8. Don't do that. You get exactly what you paid for. If you go with something like a soldering station, you've got a tool that'll last you a lifetime. Let's go through a few examples of irons that I think would be suitable for model railroad purposes. Soldering iron. This is the standard kind of soldering iron that you simply plug into the wall. This is a Weller 30-watt, 120-volt soldering iron kit. It comes with everything that you see in the picture. The iron, a plastic soldering tool, a little bit of solder, and two extra different shaped tips. This is readily obtainable at Home Depot in Canada for just a little over $40. The next step up would be a simple soldering station. The great advantage of this is it allows us to vary the temperature by varying the wattage. Now, this is a questionable feature, and really you're not that much farther ahead than you are with the iron that simply plugs into the wall. It is a little more expensive. You can get one on Amazon for about $75. And here's the Cadillac, the Weller Digital Soldering Station. As you can see on Amazon, this goes for about $167. Less than $200. You can set the temperature exactly digitally. It has a digital output display. Tips are interchangeable. I'll talk more about tips in a little while. And this is the kind of tool that you buy once and you'll have forever, hand down to your children and grandchildren. This is another alternative. Now, I'm a bit old school when it comes to soldering. I learned how to solder in the 70s, and I did it as a career starting in the early 90s. And this is the soldering station that I am most accustomed to. It is not digital. It is, however, temperature controlled. It uses a very ingenious and easy, simple technique to control the temperature. It uses a magnet inside the iron, and the tips have a magnet in them. Now, when magnet heats up, it loses its magnetism, and therefore a simple switch turns the tip of the iron on and off to maintain a temperature. You can find these on eBay used for about $100. The advantage is it's a 50-year-old design, parts are still available from Weller, and really, there's not a lot to go wrong with these. I've had one of these since the early 90s. I use it all the time. It has never failed. When I was soldering as part of my job, we had these on our workbenches. They were turned on 6 days a week from 7 a.m. to 9 p.m. The only time I ever turned mine off was to change the tip. Now, of course, Weller isn't the only brand out there. It's the brand that I'm familiar with and I trust. Heiko is another brand that is very, very good. Again, in this example, it's a digital display, so you can set the temperature. However, I would warn you to avoid Chinese knockoffs. Most knockoffs that you can get out of China look like Heiko or Weller. I wonder why. And of course, always your mileage may vary. I know people who have bought irons from China They're the knockoff brands. They work perfectly fine. It's all a matter of your personal choice. Let's talk about temperature for a minute. It all depends on what you're soldering. For through-hole components on a board and wires up to, I'd say, 22 AWG, 700 degrees Fahrenheit is perfect. If you're soldering larger wires, you might consider something like an 800 degree Fahrenheit. So what do the watts matter? The wattage of an iron will determine how fast the tip can recover. This also relates to the tip size. Think of it this way. You've got a hot iron in your hand. You press it up against two other metals. If there are large metals, such as large wire or code 100 rail, that metal is going to draw heat from the iron and lower the temperature. If it's a low wattage iron, it can't bring the temperature back up fast enough to get good solder melting, to get good flux melting, and to give you a good wet joint. If you use a higher wattage, that is going to recover that much faster. I'll show you in a little while why the 800 degree Fahrenheit tip is very useful. First, tip sizes. Now these are the common Weller tips. They're one model of tip. They have different tip models for different irons. And you can see at the top we have a conical, then what they call the screwdriver tip, and there's other various types of tips. The most useful to us is the one on the bottom, the long conical tip, the screwdriver tip, and the short conical tip. And of course, the larger the tip, the more watts you want to keep it at the temperature that you want for soldering. Of course, you need to keep the tip clean. There's a lot of opinions about this. However, never use abrasives. Some people will say, oh, I use steel wool or just a little bit of sandpaper. Never, ever do that. The tip of a soldering iron has a coating on it to prevent oxidation. And when you use an abrasive, you remove that and ruin the tip. Always use a damp sponge or what we call brass wool. The brass wool will not is not abrasive enough to affect the coating on the tip. Now, of course, the damp sponge draws heat away and cools the tip, so many people prefer the brass wool. Every time you use the iron, clean it and tin it. And I don't mean when you first use it. Every time you make a solder joint, clean it and tin it. You can use what they call a tin pot, and all that is a pot of solder that you dip your iron into. Or you can just put a little from the wire solder in your hand. Remember, if a tip gets damaged, don't try to use it. You're only going to frustrate yourself. Replace it, they're cheap. Few notes on safety. Wear eye protection. When the flux melts, it lets off toxic fumes and smoke. These can get in your eyes and burn them. Also, there's the chance of a little bit of solder splash, hot metal. You don't want that in your eyes. Don't breathe in the fumes. You can get a fume extractor for your workbench. Takes care of that nicely. Always wash your hands. You're handling a material that contains lead. Always wash your hands. And of course, the tip is hot. Don't touch. I guarantee you will, and it'll teach you real quick. Wire gauge. I mentioned this earlier. At the top, we have 14 AWG on down to 30 AWG. Now, this is stranded wire. It has its uses because it's flexible. Here we see a comparison between solid core wire and stranded wire. Again, Both have their uses, stranded wire being more flexible. So if you're using it in a situation where things will be moving, use stranded wire. If something's solid and not moving, use solid wire. So what size and type wire do I actually need? Essentially, any gauge of wire will handle any voltage within reason. The determining factor is the current or amperage that goes through the wire. The higher the gauge and the longer the run will result in a greater voltage loss. A thin, long wire is basically a resistor. So common wire sizes that we use, 28 to 32 AWG is used in DCC decoder wiring. The runs are extremely short, a couple of inches at the most, and can handle the current that we need. If you're running a bus on a large layout, you want to use 14. If it's a smaller layout, you might be able to get away with 18. And for track feeders, anything between 18 to 24 will work, all depending on how far your feeder is from the track bus. And stranded or solid, as you prefer. I'd like to talk a minute about through-hole board soldering. Here's an illustration. The blue is the substrate of the board. The yellow rectangles going around the blue are the copper pad. And of course, the yellow thing sticking up is the wire. And we see what we want to have for a solder joint. We want the solder to be smooth, shiny, and a bit concave. That's the perfect solder joint. And if it's wet, we have a joint that will not fail. Let's have a look at some solder joints that are good and bad. On the far left, we see a cold joint without proper wetting. You can see how it's balled up. It's gotten around the wire, but it hasn't flowed onto the pad. A solder joint that is sort of rough and bumpy is called a cold joint. Usually happens when the wire moves before the solder can properly come down and become a solid again. The next one, we don't have wetting on the pin or the pad. Basically, we just have a ball of solder there. You might as well just put some hot glue on it. Then we have insufficient wetting on the pad. It's again around the wire, but it has not made a connection to the pad. Next, we see probably the perfect joint. You can see the conical shape. You can see that it's shiny, and all surfaces have been properly wetted. Next, we have too much solder. Now, that's not really going to make too much of a difference, but it's not proper procedure. The next one is okay as well, a little more than the first one, but again, it still has that triangle shape. And again, on the right, we have too much solder. I want to show you a couple of videos, and there's no audio with these. And this shows some proper techniques for board soldering. There's no audio, but I will narrate as we go. And please excuse my shaky hands. As I get older, my hands shake. So here we have a typical board with components sticking through from the other side. Now, as we go through this, you'll see that I put the iron right on the joint between the base and the wire of the component. I allow it to heat up for a second, and I apply solder. And once you've done this a few times, you will see the wetting action take place. Now, the smoke that you see, I'll show you another one. The smoke that you see is not from the solder itself. That is the flux flashing off. And there we go. And you can see the conical shape. And once you get this technique down, you can see how quickly soldering goes. A board like this would only take a few minutes to completely solder up. And again, anybody can do this. It's a matter of practice, practice, practice. Now you'll see at the top and bottom, I have larger pads with larger legs from the components sticking through. So now I have to make sure that I apply heat long enough to get that whole pad covered. You see, I had to go back there, but there's nothing wrong with that. You want to make sure you have enough solder, but not too much. And it's easier to add a little bit than it is to remove, although we will talk about removing solder. Now you can see easily that it takes a little longer and a little more heat to sufficiently heat the pad to get the solder wet and flowing. So that's board soldering. What about if we had to splice two wires together? Well, this is the famous Western Union splice. You would do this in the field if you want to create a splice that will never come apart and will be reliable for many, many years. The key to this is that there is a mechanical connection. You can see the way the wires are twisted, that mechanically they're secure. We're not relying on the solder for a mechanical connection, only for an electrical connection. So why do I need to do a wire-to-wire splice? There's many reasons for doing this. You may have got a wired decoder that you need to add wires to. You may be working on pickup wires that are already in place, motor wires that are already in place, wires for speakers or lighting. You might just need to extend a lead. Now, with our very small gauge wire, it is very difficult to get the Western Union splice. So most often I resort to a simple splice, mostly because I don't need to rely on it for a mechanical connection. We don't have a lot of mechanical forces in our locomotives that would require it. So let me show you a few techniques for splicing wires. So what I have here is a two helping hands, I guess you would call it. And I have two 22 gauge wires. Now, the first thing I'm going to do is tin the end of the wire. You can see that this is copper wire. There's no tinning. You can buy wire that's already tinned. So the first thing I do is I tin the wires, and then using the helping hands, I place them so that they are parallel and touching each other. Then I come in again with the solder and soldering iron to complete the joint. Never, ever, ever put solder on your soldering iron and then bring it to the joint, except for one exception, which I will show. And you can see that this is a very shiny joint and is quite strong, but you cannot rely on it mechanically. Now this wire is stranded wire. Can be a little more difficult. Also, it's much finer than 22 gauge. And I'll show you my technique. That what you're seeing at the bottom is simply a piece of tile left over from a project. So what I'm doing here to the wire is after I've stripped it, I hold on to the wire and give it a twist. This twists the wire together to keep things neat and tidy. I place them on the ceramic tile and hold them down just with a couple of pieces of painter's tape. And they are parallel and touching. And then just with a quick bit of solder, they are joined. And you can see the residual flux. That's that yellowish liquid that's below there. And you can see that's a good shiny joint, nice and strong, won't come apart. And of course, I would cover that if I was doing this within a locomotive for a decoder installation. I would cover that with a little bit of heat shrink. Now, I said never put the solder on the tip of the iron and then bring it to the wire. Sometimes you can't have both wires held securely parallel. So in this case, I have one wire on the right-hand side that is secure, and I'm going to form a splice with another piece of wire that I have to hold in my hand. So what you're seeing me do now is get a little bit of flux, and I'm going to use this liquid flux on both pieces of wire. And then I am going to hold them parallel, put a little bit of solder on the tip of my iron, and then bring it to the joint. Now, the reason why we never put solder on the end of the iron and then try to make a joint is because as soon as we do that, we've burnt off all the flux. So in this case, I simply add a little bit of flux, and I don't have to worry about the flux core of the solder. Soldering rail joiners. Why? Well, for smooth curves with flex track, a soldered rail joint is essential. Now, always leave some expansion joints when you're doing a larger layout. That's because the rail doesn't change size with temperature, but lumber does. For short section, a soldered rail joint is easier than putting in another feeder. What you want for this is high heat. You want to get in and out as quick as possible so you don't melt ties. And of course, flux is essential here. Now, this is where the heat comes in. I want a lot of heat so I can get in there, bring the rail and the wire up to temperature, get my solder in, and then get out as fast as possible. That's how you don't melt ties. Many people believe I need a lower temperature in order to prevent melted ties. That doesn't do much for you because at the temperature that solder melts, plastic does even before that. So the only way to prevent this is to get in and out as quick as possible. Many people use wet rags or Kleenex or paper towel to draw away the heat so that the ties aren't melted. You can do that, and it's perfectly good, but that's an extra step that I don't think is actually needed. Let me show you. So here I simply have two pieces of flex track that I want to solder the rail joiner. And you can see with a micro brush, I'm just applying a little bit of flux to both sides. Now, liquid flux isn't watery, but it's a little thick, but it's thin enough to flow into the joint of the rail joiner. That's important because where the flux is, the solder will flow and have that wetting action. So I've applied a little bit of flux, and now I'm going to come in with my 800-degree soldering tip and a larger tip, as you see. I don't want a tiny little tip. And I simply go to the joint and the solder will flow in. Now you see how it's flowed right into the joint. There's no excess solder showing. You can do it on the other side. Sometimes I do, sometimes I don't. And again at the top. Now you can see at the very beginning that solder is balling up. That means it's not hot enough yet. But once it reaches the proper temperature, the solder will flow into where the flux is. And you can see on either side of this, I haven't melted either tie. Now, after I've done this, I will come in with a wire brush and I will clean it up, getting rid of the excess flux. You may see a little bit of solder on the top of the rail. And again, a quick stroke with a file will remove that completely. And as you can see, there's no excess solder there. There's no globs of solder. It's all in the joint. Now, soldering feeders to rail. We all have to do that, whether you've got a DCC layout or a DC layout. Pre-wired rail joiners are available, but they are costly. And there are many places you won't be able to use a pre-wired rail joiner. And of course, this will prevent dead spots on your layout. I'm going to show you two different methods of soldering feeders. Now, this first method, you can see how I shape the solid wire. Here I'm using 20 gauge solid pre-tinned wire. And you can see where I fold it over and then put a little jog in it. So as I put that through the feeder hole in my sub-road bed, the wire can lay right up against the base of the rail. Now it can be a little tricky to get that to do that, but you'll see here as I push this through that I have to move the wire around in order to get it to lay flat against the base of the rail. You can use a pair of pliers, the tip of a screwdriver, the tip of a file. And as you can see, this one's given me a little bit of trouble, but eventually I get it to where I'm happy. So you can see how that lays right against the base of the rail. Now again, I'm going to come in with a little bit of flux, apply that. And then come in with my solder and soldering. Apply heat, apply solder, wait for it to reach temperature, and it flows in. Now you see there wasn't a lot of solder there, and I didn't melt the ties or the spike head detail on either side. I'm going to show you another one real quickly. And again, it's going to take you a few of these before you become proficient. I suggest doing exactly what I have here. Set up a little test on your bench, practice, do maybe a half a dozen or a dozen, and then when you go to your layout, you'll know exactly what you're doing and you will have no trouble whatsoever. That's exactly how I learned to solder. My father set up a little jig on the workbench, showed me what to do, and he says, "Here, go at it." Came back a half an hour later to see how I had done. Now, once again, we want to clean up that excess flux. And I use a wire brush to do that. So now here's the other technique that I use. And Andy Sperandio from Model Railroad Magazine showed this. I simply put a bend in the wire, and then I move the wire and crush it. Now this is simply copper wire, so it's very soft. And you can see how that flattens it. And then I come in with a pair of clippers and I clip that off. And now I have an approximate representation of a spike head. Now, if you're using rail that's finer than Code 100 Atlas FlexTrack, you can use a finer wire and get an even smaller spike head. Once again, I want to make sure that that wire is flat up against the base of the rail. Here, I'm just using a little file to move it into final position. It doesn't have to be square on, as long as there's a connection between the rail and the wire. Once again, we come in with flux. Now, again, I'm using flux simply because this is such a large connection that the flux that's in the solder is not quite enough. And I want that solder to flow. And there we go. It's flowed. I'm not exactly happy with this particular one. But again, because I'm going in and out so quickly, I'm still not melting the ties or the spike head. None of that plastic is melted. And when I come in with the wire brush, you can see that that is a very small joint. There's not a lot of solder there. If you paint your track, this will virtually disappear. You can even solder feeders on the inside of the rail. If you're up against a backdrop or the back of your layout and can't get around to solder the feeder on the outside of the rail, by using this technique, you can solder feeders on the inside of the rail. I'm very happy with that joint, how it went, how quickly it flowed. Now, again, I come in with my wire brush, I clean it up, and you can see that that joint doesn't go anywhere near the railhead. It will not interfere with the wheels of locomotives or cars. And here I am using the flange gauge on the NMRA gauge to show that there is no obstruction whatsoever. One last time, I'm going to show you how I do this spike head. Andy Sporandio even does it through the plastic tie. He removes the cast on spike head, drills a hole through the tie, pushes the wire up, and solders directly to the rail without melting the tie. And once painted, you don't see it. Again, practice is your friend. You do this a dozen times, you can go to your layout, start soldering feeders, you'll never have problems again. Desoldering. Sometimes you need to remove solder. These are three methods of doing so. At the top, we see the solder sucker bulb. This is what I was taught to use by my father. Always used it, and with practice, you can get proficient at using that. On the lower left, you have the solder pump. Many people swear by this. I swear at it. I have never been able to get a solder pump to work. And finally, you have desoldering braid on the lower right. This stuff is magical. What it is simply a copper braid that's impregnated with rosin. You apply it to the joint, apply heat, and it will suck up or wick up the solder in the joint. That's all I have for you today, and I welcome any questions you may have.